Hi friends, welcome back to the channel. Today I'm going to solve an exciting problem from the topic of vibration, mechanical vibration. This question was asked in GATE 2020, but there was an error with the options what they had given. But let's not bother about that for the time being because we have a good problem which will test our understanding of the subject to a certain extent. So it's a really nice problem to do on your own. So I request all of you to pause this video and read the problem very carefully. Try to do the problem on your own, and if you are stuck at somewhere, then come back and listen to the rest of my video. The first step is to boil down what method we should use, whether we can use energy method, whether we should use Newton second law. There are all options. For the time being, I will use Newton second law, but even if you do with the energy method, you will get the same answer. So here, I think the key thing is you need to isolate a system initially, then apply the external forces what are acting onto the system. So the first question is how this system is going to vibrate. So this system is going to vibrate predominantly in a mode like you say this road will rotate in this direction about this mean position. So that is the kind of kinematics that is involved in this particular problem. Once you know the kinematics, then the next question is, as this massless rod is rotating about this hinge point A, what are the kind of external forces does the system see or does the system get subjected to? So that's the next question we need to answer. Once you know all the external forces acting on the system, then it's fairly easy to write the equation that governs the motion of the system. So the first step, understand the kinematics. Second step, understand what are the external forces or figure out what are the external forces that are acting on the system. Then write the equation of motion. So let's get started. So the first question is, what is the system composed of? So here I have isolated the system here. So as you can see over here, this is the system now under consideration. We have two things. We have this massless rod as well as the disk of mass m. So this is our system, and how it is going to move, it is going to rotate about this hinge point A. So what is going to happen is there is a spring over here, the first spring, which is having a stiffness of 2k. That this will get compressed and it will apply a force in this direction. It will oppose this motion. Similarly, what happens over here? Here we have an inextensible inextensible cord. So, and here we have a spring. So what happens is, as this gets rotated by theta, this whole point will move down by L theta. That comes from the geometry because as it gets tilted this way, this point, the point B, will move downward and it will move by an amount given by L theta, where L is this length and theta is the rotation undergone by the massless rod. Make sense? Now what happens to the inextensible cord? The cord cannot extend, so what happens is, but there should be a change in length for the cord as the pulley or as the disc comes down. So that deflection, which will be twice of the downward motion, because we have this rope over the pulley, so the displacement felt by the spring will be 2 times capital L times theta. Make sense? So this is how the kinematics looks like. I understood how the system is going to behave, and I understood what are the deformations felt by each of the springs that are there in the system. Clear? Now going ahead, so here, as I have explained before, there is a spring 1 here and there is a spring 2 here. Now drawing the free body diagram, it will look like this. Very simple. 2k is the stiffness of the spring, delta 1 is the deflection felt by the spring 1, and delta 2 is the deflection felt by the spring 2. One thing to remember in mind is this is acting at a distance of L by 2, which is quite obvious, but this is acting at a distance of L plus R. This is this particular force is acting at a distance of capital L plus little r. And don't forget, little r is L by 4, so which is again a fraction function of capital L alone. Now, these two deflections I explained, this comes from kinematics. This I already explained just before. So this is fairly easy. Now we go ahead and write the equation of motion. See, the motion is pure rotation about the point A. So the equation of motion is Newton's second law for pure rotation or for rotation about a fixed axis. And the rest of the things are fairly easy, but I will go through this equation as well. So this is the stiffness of the spring, this is the deflection felt by the spring 1, and this is the distance from the I will tell you, like, this is the distance. Actually, this is the L by 2 is this distance we are talking about. We are summing, taking moments about this point. So the distance between the force and the hinge point is L by 2. Similarly, here also the distance between the force and the point about which we are taking the moment is capital L plus little r. Make sense? These are all good when you there is a big assumption, that is theta is small. Okay, theta is small. That's why we are able to make all these assumptions and all this. We are solving this problem for small vibrations. Similarly, this is the stiffness of the second spring. This is the deflection felt by this second spring, and this is the distance between the second spring force and the point about which we are taking the moments. Now some simple mathematical manipulation will get us here. So the natural frequency of this system can be simply written as root of 3kl square divided by Ja, where Ja is the mass moment of inertia of the system about this point. The road doesn't contribute anything to the mass moment of inertia of the system. Why? Because it is massless. The only contribution comes from the disk. The disk is having a moment of inertia about its own centroidal axis, that is at B, because its centroid is at B, that is mr square by 2, a very well known formula. But then we are not summing our moments about this point capital B, we are summing up moments about the point capital A, which in turn tells that the actual polar moment of inertia or the mass polar moment of inertia of the system about this hinge point is mr square by 2 plus mass times this distance capital L square. But if we plug this thing like little r is equal to L by 4 and all, then we will get the right answer. But in option, that answer is not there. So what they have done is they have made an assumption actually to get the answer what it is there in the option. They are neglecting this term in comparison to this, which is a sensible guess. Like they are telling if you take the correctly, if you take the polar moment of inertia or the mass moment of inertia exactly, then it will amount to something like if I am right, I think there will be 33 ml square by 32, I guess, if I think I'm right. So this will be the our final mass moment of inertia about the point ml square, the point A. But they are assuming it is as good as ml square, which is a valid guess. Once we plug in that value over here, then we will get omega n is equal to root of 3kl square divided by Ja will be simply there is no 3, there is ml square, which gives us natural frequency is root 3k by m. Make sense? So there are a couple of things you need to keep in mind while solving this kind of problems. First, isolate a system. The system may be comprising of a rod and a disk, as shown in this example. Then understand how it is going to deform or how it is going to behave. Then understand the kinematics of the system. As in this example, we said the deflection felt by this spring, this S2 spring, there's a spring over here, that will be twice of the deflection felt by the point B, because this rope is wrapped over the pulley. So as it goes by, let's say, delta, then this spring has to extend by 2 delta, because this is an inextensible rope. This is an inextensible rope. Okay, make sense of the understand the kinematics, then understand what are the external forces that are acting on the system, then write the equation of motion. Once you have equation of motion, then things are fairly easy, because we always know if we have our equations of the form mx double dot plus kx equal to 0, then natural frequency is given by omega n is equal to root k by m. Makes sense. So it was an interesting problem. Very sad that they got the options wrong in the actual gate exam, but it's not an issue. If someone gets here, he can pick the right answer from the all four available options. Thanks for watching.